So thank you very much for inviting me. Thank you very much for being here. If you are searching for this kind of competition, I will not speak about it. So it was quite interesting to listen prior to the talk on natural language processing, natural language understanding, which is quite important for our society. But at the same time, you have to know that more than 50% of our brain is dedicated to computer view, to actually to vision. If I'm saying that my laptop is there, you have to search for it. You don't know where is my laptop. But if I'm showing that my laptop is there, your eyes will actually localize the object. This is the powerful tool of the computer vision today to actually take this universal approach of the people, which are not based on the language, and we can use that in the computer to do more things. So my name is Florin Manaila. I'm here to present you some use cases where I've been involved, and some other colleagues of mine have been involved, some of the technology behind the scene there. Feel free to put questions during my talk. I don't want to leave it at the end because then you will forget those kind of things. It's just an interaction, right? So feel free to do anything else. I'm spending all my time in the last 3 years to actually move IBM inside and customers to more self-aware runtime, which means that we need more intelligent solutions that are really able to observe the environment and then adapt to that. So for example, just imagine whatever we have built in our society until now, we call it traditional runtime. It's like your mailbox, you create some rules. Now this is from my family, this is from my friend, this is Gary, she's from the office, I don't care, and it's going to the folder. This is statical rules. In the moment when you want the system to detect and tag automatically the emails, you need some intelligence behind that, so some algorithms, right? So by the way, we have data scientists here, or mathematicians. Okay, few, all right. So just pop in with some cool questions or completely if I'm wrong with some others. But in general, we want to make decisions based on the evidence. This is what people can do if they don't get angry, right? So by doing so, we have this, and I think I'm just going to explain it very well, if I understood correctly, the artificial intelligence field, machine learning, and then we have the deep learning. So for the machine learning is actually used in the majority of the banks in statistics right now. We have to do a lot of feature extraction. We mean that we have to know the domain. We have to understand the domain. You say, well, I want to extract from this kind of data, this and that, and then I want to do a logistical regression. So I want to split that. I will going to speak on use cases where we use deep learning and those neural networks, where in general you want to feed the data into the model and then the model to extract the features and identify whatever you want. Either do object detection, classification, semantic segmentation, and for example, image reconstruction. So, okay, the question that I want to say here, do you know how AI will impact you? Have you asked yourself this, or have you read a book for that? Who's using WhatsApp? Who's using Google Maps to find new ways around, new restaurants, or almost everyone. So I even have a friend that has at home Alexa, and I was speaking with his wife, and it's really scary because Alexa sometimes is not recognizing her. So he's now stopping the light and goes. So people, they start adopting those kind of technologies in the job, in the house, in day-to-day activity. But the question is, how we can really, bring this further and to be more safe, more secure, and how the society can really embrace that. So a couple of things here that I will want to explain to you right now. So a couple of use cases where we are involved a little bit. One of the use cases is that automotive companies right now, they want to put the AI in the cockpit. So automotive companies, they want to have autonomous driving, or ADS, autonomous driving assistance, and as well AI in the cockpit to detect those kind of things where the driver is distracted and so on and so forth. And the reason is here not because someone would like to pay for this, that the car to understand when it's actually drinking the coffee, but because when you want the car to do some more automated things, and then the car has to pass the responsibility back to the user, you have to understand what the user is doing. Is actually with his girlfriend in the back there, or is in the front? So those are some couple of key things which are coming probably if you have a new car. There are some couple of features there like gesture recognition. If you see some people in the car waving the hand like this, or should they try to put music which is not working? So be aware of that. So that's one of the things that is happening right now in the industry. Another thing on the car is the car damage classification. There is as well another implementation done by AXA in France, trying to detect the people that most likely they will have a car accident next year. Using Twitters, feeds from forums, and obviously natural language processing is one of the things that is actually driving this. But on the computer vision, the goal is, when you have a car damage, to use an app, a mobile phone, make pictures, send this to your provider, will process this automatically, and based on the finding, will say, well, it's a serious damage, come out, we're going to inspect more. What means for them is that they can retain more customers because they can make them more happy about the process, or they can detect much faster the fraud. Because when you make the picture, you have to do it when you have accident, so they can get tagged on the GSM location, position, and all this, and they can have as well events from that region with the policeman and so on. So it's quite interesting, powerful tool. Now, if you look on the factories here, you see that we can apply, this is object detection. So we want to apply deep learning to detect objects like vests, helmets. So we tag them with the boundary boxes here. Or for example, roofs or anything that you can imagine we can tag, right? So there are factories where they say we want to have employees to wear all the time all these kind of things. So moving further, this is another use case, I think this is from Spain, where they were implementing, as a company, they were implementing the deep learning to actually identify those kind of tracks, which those dangerous transports on the highways. Because some of them, they don't have authorization to be there, and if there is a particular track in a particular segment, you want to understand if the police has to be aware on that particular case. So it's another good way to enforce some laws around that. And the same thing we can apply for urban sound classification, probably not in Rome, but in more quieter cities where it's drilling all the time. So all the CCTV cameras in general, they have a microphone. So we can take the sound from there and we can analyze the sound and we can say if dog barking or someone is drilling or whatever. So in a couple of hours, we can say during the night if someone is drilling, this will automatically trigger an alarm to police to come and check in that particular area. So we will not wait for someone to call to the police, hey, someone is drilling here, and all these kind of things. So this can be done with the computer vision. Another use case is how we detect from X-ray images objects. And particular use case is on the airports. You can see here where we can detect whatever you can imagine. So we can train a neural network to recognize those objects. And in particular, we can even go further to have those big trucks to be scanned upon while they are passing to the highway. So there are some couple of highways probably you have seen where you have to pass on a very low speed. So they have some kind of gates, so they are doing scanning there. And if they do scanning, they actually can detect even guns on this side, kind of size. So you can write the algorithm in such a way that you don't get the image, but you get only the result. So this is as well something that can really automate this kind of industry of scanning trucks, planes, and everything. And the technology is out there. We just have to automate in this way. And in the airports, the problem is those nasty cases where two people that are going there together say, what is in this bag? Maybe it's a razor blade, or we should check it more. So, and there's a long queue over there. So we can automate these annoying use cases. And here's an example we built for a proof of concept where we train a network actually to do the same thing. So to recognize guns, razor blades, all these kind of things from those X-rays. And what was interesting in the first time is that we tagged only those kind of guns initially, but then the network is trying to extract the features and will recognize the gun even if it has a different shape. You know, obviously I think nobody's crazy so much to carry a gun when it's going to the, but who knows? You know, people, they can do a lot of things. So this is just an example where you can use X-ray to detect objects. In the same thing, you know, hospital, they can implement this on X-ray to detect, you know, things that the small children are eating. So they can have this immediately without, you know, too much analysis there. So again, this is another cool thing. Now, if you look a little bit more further on the security side, there are still some institutions where they want to prevent actually guns there, you know. Obviously, if you speak with someone from Texas, you say, yeah, they're laughing, everyone has a gun here, even the children. But if you look on European Union, in general, in Europe, there are, let's say, like modes where you should be, you know, you should issue a warning if someone has a gun in the mode. And if it's not a policeman or if it's not a military person. You need to be aware of that. So we can train neural networks to recognize such cases, people with guns in the head. So here's a nice model that we applied on a movie we find on the internet. All right, just to see how this can work. And obviously, banks, some on the large things, they can be using this technology. What we found out there while building these kind of models is that always the cameras in the banks, they are different in different angles. So you have to feed the data set, the images from that particular angles to actually identify the objects. We took those images to train the network from a lot of movies which are on YouTube. You'll be amazed how many movies we have with guns. Amazing, right? So I don't know what's happening with this world. And then this is just an example of how this technology. Why this technology is interesting? Because many companies, they have the CCTV cameras. I will not mention London, United Kingdom, where CCTV cameras like water. But in general, all the institutions, they have cameras in place. So the only thing that we need is just the feeds from there into a system that we can do some classification of the detection, any kind of things like this. So this is just an example where we can take this. And if we a camera will see a couple of guns in some scenes from different angles, automatically it can trigger an alarm there or to someone, right? So again, this is quite easy. It's not this model that we did it for demonstration has around 87% accuracy over a small data set. But this can be really enhanced on high accuracy level. All right. Another thing is drones. So anyone has a drone here? 1, 2, 3. Okay, good. So when you have a drone, you know that you can sneak on any neighbor, you can sneak on any institution to take a look what is there. Even if there is an airport, even if obviously if you have a good drone and it's not that one which is with flight control. But in general, the drones today, they can carry almost anything, from bombs, from, if you look on the internet, you can buy even drones that they can carry a gun, so you can trigger that gun in a particular area just from remote. So it's interesting what can happen with this drone and how this drone will transform our society in the future. But there are some concern how I can prevent drones to fly in a particular area, especially those drones that are, let's say, we call it sport drones, that you can use them for racing, right? So they don't have GPS in there. So if you have an institution that has those CCTV cameras, we can create a model to detect those kind of drones and even classify the drones, small, medium, large, or governmental drone, and then as well to count them. You will be a better, but sometimes the guys like you, maybe you meet with some other guys with drones and they do a race or say, okay, let's sneak the whole area here, which is military area, and then upload it for YouTube for some guys to have cool stuff. And I like it. So we train a model, actually I did this, 92% accuracy to detect those kind of drones, and this is just a result here of putting a camera, steady camera, and then detect this drone while it's flying. So the goal here was how we can, first of all, detect the drone if you have a CCTV system, and the second is how you can detect and localize the drone, the distance to the drone. So we have the focal point, we have the resolution, and if we have 3 cameras spotting the drone, we can do triangulation to get the position of the drone. There is a question? No. All right. So interrupt me, Tony. Yeah. So this is what we have done, and it can be used for security purposes, especially in the airports, those kind of things.
Is it predicting the direction of the drone because the square anticipates the movement?
No. So in this case, we just detect the object. But if you want to detect the position of the drone, we need 3 cameras. So we can detect then, we have the 3 axes, so we can detect the relative position with these 3 cameras because we know the GPS location of the cameras, so we have this triangulation. It's the same like mobile phone, like it says. There are some other techniques where it involves a lot of radio frequency there that is like a radar that will detect drones, but if they are small drones, there is no way to detect them. But we can try to even detect with 20 seconds the direction of the drone, where the drone will fly. If it's flying, there will go there. Just an example. All right, so another use case was, okay, where are the images for? So if you look a little bit on Sentinel-1, which is radar from European Union satellites, Sentinel-2, which is giving those kind of images, 7 meters resolution above the ground, you can have real precise images, and they are really all of them available to any European governmental agency on Amazon via a portal. Yeah, it's called Sentinel Hub portal. So what you can do is, you can take any image from Google Earth if you want to test that. You can snap that, and then you can feed that image into a model, and that model will tell you, well, it's a plane there, it's a dense area there is a factory there's a military station there, and so on and so forth. So you can use that for military planning, you can use that for agriculture, you can use that for insurance. Just give you an example, on agriculture, we can detect the water on a particular area and do segmentation, so we can then measure on that particular area how much water is. And when someone is claiming, say, hey, my crop has been destroyed because too much water, give me the money, you can actually check with a single click my GPS coordinates. So this is how we can use the remote sensing for classification or segmentation, or we can even detect the crop status. So if you have crop, based on the color of the crop, there is an index called natural vegetation index, obtained by different infrared and wavelengths. We can actually detect the crop status if it's healthy or not from satellite. So all these kind of things are really used in agriculture, insurance, and in real estate is actually used to detect, to predict actually what will going to happen in particular area in terms of development, houses, industry, those kind of things. So they can raise the price probably. Another thing, this is one of my preferred one actually shop from Eastern Europe that they're selling a lot of products, electronics, anything you can imagine. They have an in-store, and actually they have as well partners selling products from their in-store. So one of the question, or the problem that they have is, when you upload a picture, someone has to verify the picture of the product if it's not containing, let's say, a lot of green shades, or that picture is correctly done, or for example, doesn't contain sexual content or something. And they had something like 1 million of images per month to process, right? And they came to us and say, can you do something? Yeah, it's very hard. Can you do something? Can you create a model to detect watermarks, to detect unclear or autofocus or blurred images? So we built this for them with close to 89, 88% accuracy in classification. So the goal was like, we expose an API, you send your image before uploading to the website, doing the website, we say yes or no, it's normal, or it's actually has contained watermark. If it's watermark, then it's dropped. You cannot actually store on the website as a product image. So quite interesting for e-commerce websites where they can really enforce and actually bring more quality to their users. Because when you buy a product, you expect the product from the image to actually to be the same that you want you're going to receive. All right, another one is actually for classification, people that they have badges in the offices. You would say, who the heck would actually want to use this? Well, you will be amazed that there are some governmental agencies where whenever you leave from the office, you have to actually take off the badge. Right? Because they have a policy where they don't want people to know that you work for NSA or whatever, right? So they have the cameras where actually they enforce it. Outside, inside, so for them it's quite easy for them. So this was an example that we have built, and you see people without the badges. And this is something we call class activation map, where the neural network is getting this map and saying that here in this region in the picture, identify the object with, in this case, with the badge. Right. All right. Then, if we move a little bit on the medical field, there are a lot of opportunities there. So a lot of people actually are doing a lot of studies there. There are a lot of research papers, many people. So I actually tried to tackle the breast cancer classification in the histopathology, where my goal was, okay, if we have labeled data sets from doctors, the question is how we can do classification of the cancer. And I will actually try to explain you a little bit the whole pipeline and give you a demo. If you are on Wi-Fi, please go off the Wi-Fi because the demo will not work. Or I can wait. All right. So this is my my work which I presented recently to one of the special events regarding this. So if you try to understand in general, when you get the news, the bad news that you may have cancer, either it's very normal, the question is how fast you can be diagnostic and how fast you can get the diagnostic and how fast you can get the treatment. And in general, you have this, for breast cancer, you have stage 1 where you get awareness, you went to the doctor, and so on, and say maybe something, let's do some investigation. Then you get this stage 2, which can take 1, 2 months, 3 months, depending on the country, depending on the case. And then stage 3, where you get access to the treatment, right? For these kind of cases, we have, okay, this sometimes is not working, we have this scheme. So the step 1 is, okay, is clinical, thing. So you go there, you get, visit the doctor, you say, well, maybe something here, let's do, let's say, mammogram. Maybe it's not the time, but let's do it to be sure. Then you do a mammogram there, you have to stay in the queue, but this is a very fast process. Then generally they see something there, they say, well, okay, then we have to do an ultrasound to be sure what kind of tissue is there, at least as an idea. And then if they still are not clear, you have to do an MRI. Sometimes the ultrasound is actually still, so you have to go to the MRI. On the MRI, you have a problem because, first of all, on MRI, not only that they detect the tumor, but they want to measure the tumor. So we need to have a very good doctor that is doing this. And if you have a doctor that has hundreds, let's say 12 or 16 patients per day, multiply by 5 and so on, that doctor will be very, very stressed always. It has a huge pressure on it. And if that doctor is actually identifying the problem, they will say, you need to do a biopsy, for sure. So you have to go there, they have to take a tissue, and then they analyze that tissue on the microscope to identify what kind of cells are in there, and then to issue the lab test. And this process can take 3 to 4 weeks. This is really, because this is crucial for the treatment, because based on the receptors, based on the prey, based on the type of the malignant, then they will give you the treatment. So I was trying to concentrate how I can accelerate this 3 weeks, 4 weeks process by giving a prediction to the doctor, especially for atypical use cases. And you see here, this is the breast cancer diagnostic 5-year survey rate. This is coming from National Cancer Institute in UK, where it said early stage diagnostic 91% survey chances of survival, and early stage, advanced stage is 16. And I will explain why. So, in the beginning, when you go, if you have something, if you do those regular things, you get 1% survival rate, then no problem. Then in general, people, they go 98% survival rate when they get something here, and they see, okay, I have OBC. And if you are fast enough with the diagnostic to actually avoid to move in the survival rate, this case where you go to have some links, or on the last one where the cancer is spreading in the whole body, and typically for breast cancer it's lung and brain, you are lucky. So it's very, we know, I'm not commenting why you do the treatment or what kind of treatment. I'm trying to help the diagnostic process with the drug. That was the goal here, and to see if we can improve something and if this is useful and is working. So one of the questions was how we can accelerate the pipeline. So in this case, in general, we learn by examples, right? So how we learn, we explained a little bit before with examples. Here's an example of a neural network where we send a lot of images here. We have, this is the input layer, and then the first layers we call it hidden layer. They will try to abstract the image to identify the shades and so on and so forth until they will create different kind of, let's say, elements. And at the end, we want to get the classification. It's a cat, it's a dog, or in our case, it's Benin or Mali, and what kind of type, right? So, and the way that the network is actually learning, we don't teach the network to actually learn, we send a lot of images, labeled images, and we say, hey, we have 1,000 labeled images, 30 images for testing, figure it out how you can learn the feature and identify correctly. This is what we do. So what is actually going into the network is the data, so the images, then we have the model, and then we have the computation based on accelerators. And I will move to the breast cancer diagnostic pipeline. So we have seen the stages, and in general we have the images from the mammography, have the images from the MRI, I didn't include here the ultrasound, and then you have the histopathology images, which actually creating them report. So the patient is actually you have all these data as a patient because they will give you DVDs and CDs for that. And then what we want to do is to process those images because are in a specific formats like DCOM and IF, and then to have a model that will do the classification and will say to the doctor, maybe it's this kind of thing. It's judgment, but we predict that with X percentage is this disease. So moving forward, we need to actually ingest all the data. We create it here, then we have to format the data in JPEG, PNG file, TIFF, whatever, to process them with the neural network. We cannot use DCOM file formats. And we create those data sets for mammography, MRI, histopathology data sets. And then we want to actually feed everything into accelerated solution where we want to do labeling, verification process for doctors and so on, so we can train those models here, and the doctors can then further validate the models. That's the simple goal. And at the end, we want to actually have an image coming from a device. We want to classify that image being a tumor A, B, or being something, normal, or negative, we call it. And then based on that, we can say, well, okay, next step is to do object detection. Where are the cells? Semantic segmentation to actually measure that, especially there are cases where you have brain tumor where you have to do very good segmentation, and then localize it and do the sizing and actually then give some information like tumor type prediction, tumor size prediction, and then tumor description, and that's it. And then is the doctor decision to judge if this is correct or not, and then to recommend the treatment. So I will skip the hardware, just move to the demo right now. So just just to mention a few things, I have used in my experiment this data set from University of Brazil, which was labeled data set for histopathology. I'm not a doctor, so I asked them to give me this data set which contains 9,000 microscopic images of breast tumor labeled. Yeah, so this is what they have, and this was actually labeled by them and then assessed by another institute. So we have two entities of the same data set saying, this is it, right? All right, so how they collect it? They collect those images from, obviously from microscope. They have a camera. This is the old data set, I think has 4 years now, or 5 years. And our goal was there to actually, I created those categories here, Benin and Milan, and in each category, adenosis, fibroma, tubular adenoma, which is one of the most common cases, or for Milan, ductal carcinoma or lobular carcinoma as well is one of the, let's say, most common cases here. And they give us images, 40% magnification, 100 and 200 and 400. I have used for classification the 400 because we have a higher, let's say, view of the cells. But we can use then further the 40x magnification to detect actually the cells, right? Because you have better accuracy. But the demo is actually when you get an image to pass it to a neural network and then do the classification. And the way that the model will actually work, by just sending him a lot of images, we'll try to identify the pattern in a particular class. And if we identify that pattern, we'll say, well, I have this pattern in that image, which means that that image is actually a lobular carcinoma. Okay, so I'm going to go to our PowerAI. So for this, I was using the one of our products, PowerAI Vision. This is not very important. This is another case we will try to count the cells. And I will, okay, so initially I had, I'm sorry, this is a bad resolution, but we have to work with it. You see here the categories, so we have B is coming from Benin, and M from Milan, ductal carcinoma is here, lobular carcinoma, all those categories are here. And in each category I can click and we'll select the images. The initial images, they were not quite enough, so we had something like 1,526 images at 40x magnification. But we add them, and this is Benin adenosis, and we say, okay, let's do a training. Even with the hyperparameter, with fine-tuning of the network, let's see where we can go with those images. Because maybe you have here so many times from marketing guys, you need so much petabytes of data sets. It's not true for this kind of work, especially for supervised learning. In the natural language processing, it's a little different. All right, so, okay, then we train a model based on this. I would just want to go and here, this is the first model that we train against this data set. It's very important in this case to have correct labeled data sets. And initially we went to 87% accuracy. Let me zoom that to see. You see 87% accuracy, which is a joke. Nobody will want to use this, right? So we said, okay, how we can, and then we have some information here on the loss and then on convergence and test accuracy because we have a couple of images that we test the model and so on. So how we can improve a model if we don't have more images, right? So we said, okay, if we have this problem and I want to go, because here if you have more images, you can get better results. So we went, okay, we have these 1,526 images and we want to do data augmentation, which means that if we take images, we'll try to flip them vertical, horizontal, add blur, sharpen, all these kind of things. Which in general, the data scientists, they use this, they use OpenCV, open source code. But obviously you have to understand the data that you're working because you cannot apply all of them. Right, so we choose a couple of them by try and match and so on and so forth, and we came up with another data set that has 12,000 images. Right, so you can see here those images that they are with are coming from augmented, are not the original ones, which means that if I have a problem, I can remove them and then try to do another training. So we said, okay, we have now so many images, and if I go here on the categories, you see here I have more images right now for each category. So let's say, okay, let's do another training and see where we can get even with the optimization. So we went up in, I think 93% was my best score. I cannot go any further with those images because then if you augment more data, then your model is overfitted, so you get garbage. And you see this is the accuracy. Training loss, you have some information here, and then the errors. And after you do this, in general, you want to validate, which means that from all the 5,000 images that I received initially, I keep something like 50 images to be tested. I didn't give them to the model. So the model has never seen them. So, okay, we deployed this for the production. Then we create an API. Hopefully, okay, a colleague actually provides something I want to delete. So I have to deploy it. This system is in US. I'm going to the model here and take the 93%, and I will deploy this model. When we deploy the model, we have to wait 2 minutes. When we deploy the model in general, what the system is doing is actually taking the model, creating a dedicated container for the production, and it's exposing some APIs where I can send the images directly to that one. Nobody will modify the model. This is what's happening. So let's deploy it once again. We have to wait a little bit. Any questions so far? A couple of minutes, 1 to 2 minutes. I have this as well offline, but I want to show you live. It's much better. I'll try to do it again.
What kind of model do you use for
Okay. Google Net Scan I use for this. So I will write the paper.
For the segmentation stage, what kind of model?
Well, this is not for segmentation, it's only for classification. So yeah. All right, so here I deployed this model with 90%, 90% accuracy. You have seen it. In general, this will be displayed something like this, where we indicate to the developer an API endpoint, so they can send to any device, any app, anything to this API, and they can send the image. And then I want to actually test right now the images by uploading the images here. So I have some couple of images that I train them, use them for training. Let me make it smaller, those things. And okay, I have them here. So I have here the testing images, and I have to type. And running, I will try a couple of things, like figure out the NOMA, and I will try to take an image from here and put it here to see if everything is okay. So first of all, should expect here that the network should identify figure out the NOMA, then so if I'm looking here, this is what the network will see. Obviously, this is not one image. You have to send more and more images from each class to really verify your model is really accurate. And if I'm taking another one, and then we switch to another class, obviously, there is a false positive always right there. So whenever you see here 100% accuracy is not really 100, it's 90 something, 99, 98 something, because we don't measure the false positive here. Another thing here you see, this is rather number 91% accuracy is always trying to identify the class activation maps, which are identifying the class. I'm trying to take right now another case from Milan, let's say Carcinoma, and upload this here. Yeah, so there are some images where you get 83% accuracy, some where you get 90, depending on the type of cells and how. I will take another one. You see 85% accuracy in the same class. But this is in 1 second. The system is in US, I have to upload it. But if you have it on site or somewhere in Europe, when you send an image, you'll get an answer. Right? So you don't expect, you don't start call for some colleagues that, well, I have a strange case, I don't know what's happening, and then you have to wait. When you get from the microscope, you can get this. Right? So this is something we see, we have seen that the GoogleNet CAM model is actually very good for this. Obviously, there are some other models, but this is what I have personally experienced.
I'm really interested in this thing. So once you manage the argument and you get focus on the image that you collected and you present to the training, what are the steps that get you over here? I mean,
Right.
you took a model, a pre-existing model, and you picked some parameters, figures, and
Right. So that's a good question. So in general, when we have a data set, go here, we have an option to do a training. Here, train the model. And you have here on the train the model some advanced options that the system will do, like how many iterations you want the network to see, how many test iterations, how many intervals of iteration, and then there are learning rate, if the network wants to learn faster or not. We use a transfer learning as well, so in the model that I used, we had a pre-trained network, and during the training, we just adjust the weights based on the data set that we have. Obviously, let me show you something. When you go to the models, let me show you another view. You will see here some field called method, where you don't have nothing here. Nothing is like what we provide by default. And then if you have a data scientist that really knows, what is behind the scene, we just fine-tune the network to get better accuracy from the data set that we have. So it's just a iterative process. In general, you spend more time in actually fine-tune the data set rather than just doing the training. Training, you push a button and then you wait. If it's not good, then you change something, and again. But having the data set labeled correctly, the right data is very important. Sometimes we have a customer give us a data set, everything is labeled. This is for mammography, and it was like, we could not reach more than 80-something%. There was something wrong, and then I started removing classes one by one. And then we found out that there were a couple of images in a particular class for mammography which were not supposed to be there. It was by mistake, or who knows. So we say, what's going on with you? Can you take a look again on this? Those networks are dummy, If you give them garbage, they will give you garbage. Right? As human, we can augment more things and so on, but they are very good. If you give them the right thing, they are very good on actually giving fast results. This is what I want to understand. All right. More. So in general, deep learning can apply in all this industry. It doesn't have boundaries. And what makes this very interesting is, and especially now, because it's not new. In 2011, when it was the first contest, we had 26% errors on the best machine learning algorithm. Right? By the way, do you know what is the human error when we augment things in cognition? Please try. Data scientists. What is the human error? So in a daily job, whatever you do, you have an error. What is that error in your board? 40%. Okay. 50%. Wow, so much. 20. Okay. I will show you 5%. So a human expert in a particular domain has an error of 5% on a daily job, under stress and so on and so forth. If you take that person out of the vacation and say, let's do something right now, cool, probably will have 1%. But by default, it's 5% according to the research papers which are out there. So what's happening is that in 2016, we went with a new deep learning-based algorithms where they were offering 3% errors, which means 97% accuracy. So this is actually changing the game. This is what is very important. So I explain you how we learn, that we learn from repeated practice, and I want to explain you a little bit how we do deep learning in computer vision. Any computer vision specialist here that will try to explain this? Okay, I will try to do it, but I know that there are some. So, the question is how you can teach a system to recognize a picture, in this case bike. For us it's very clear, that's a bike, that's a bike. This is, okay, probably a destroyed bike. This is maybe an art, but still is a bike. And that is from starter over, yeah? So, the computer, the systems are different because they see pictures. This is Felix the cat. I have a cat, which by the way is Felix. That's why I choose this picture. So they see the pictures as matrices, and this is a picture with 35 by 35 resolution, and in the corresponding in the computer is a matrix, 35 by 35, remember from school, where the system, if it's black and white, is getting 1 for white and 0 for black. That's it. So how we can teach the system to recognize those kind of things? So we created this concept of neural networks where we have these neurons, and these are mathematical functions here where we have an input and an output. And we expect to send the data here and to get the result here. And there is always, we call it training, is a forward propagation where you send the image, you get a result, and then you adjust those weights to be better. And then you come back in a backward propagation. This is one of the simple ways to explain deep learning. Right? There are as well some other kind of things. So the result is actually this you have seen. So how we do it is that we define a kernel. This is, by the way, Leia. Search it on the internet. You'll be amazed how beautiful it is. The full picture. Right? So data scientists, they know who is this. So we define a kernel, and this kernel will go in the picture row by row in general and get some numbers here, right? And we'll create another, let's say, matrix which is much smaller. So we take it like this, smaller, and then we actually create a category. So we have 3 types of methods today approaching deep learning. One is supervised learning, one is unsupervised, and one is reinforcement learning. This is the most powerful today. The way that I used was supervised learning, where I said I have labeled data sets, I give you 2 trainings, I have some testing, use it, which is the most safest one, right? The reinforcement learning is something where, it's like a reward, it's like the children, go and bring me the water, I can bring you something else, no, sorry, I cannot give you any chocolate. And the same with dogs, the same with train the dogs, the same process, right? So, this is what we do. So if you look on the AI infrastructure, what you need, right? It's quite important to understand these concepts behind in order to understand, because if you're going to get a salesperson say, hey, I have the best system for AI, it's coming from IBM, don't believe it. Because everything has a purpose. So in general, we need accelerated infrastructure, systems and storage. And then when we move further to the stack, we need something like to create those data lakes and store where we need to store the data. If you have pictures from, or images from 20 years back, you will have to bring them because it's valuable information for you. And then you actually need to have distributed computing to actually glue this together, and we use in general MPI, multi-passage interface, coming from high-performance computing, so nothing new, or Spark. And then there are a lot of open source frameworks. You are working with what? TensorFlow. TensorFlow. Okay, that's cool. TensorFlow, Caffe, PyTorch, and so on and so forth. And at the end, we have to deliver an application. So we need some APIs that the developers will really understand this madness. So one of the distinct problems here is how we transfer and prepare the data. That's a very key thing when you design something. Obviously, along the line, there are a couple of problems like, how you can identify the proper use case. We spend with customers even weeks to identify the proper use case for them, right? So it's not something that you can take it out of the box like a product, WebSphere or Oracle or whatever, and say, here's the solution for the data here. It's not like that. So we are trying to tackle all these kind of problems and say, how we can reshape the infrastructure, how can you reshape the software stack to tackle those kind of issues at scale. So starting from the things, 3 pillars, data. If you don't have data, forget about it. Yeah, we just store it. Then models, you can find a lot of things on published, some of them for more serious things. You need to have data scientists that they have to work on them. And then obviously you need to have computation, accelerated systems. So we have to look at a little bit what we can change. This was a work that we have done with Open Power Foundation. Google is part of it as well, where we say, okay, everything which is running, machine learning, deep learning is running on accelerators today, right? So we have the open frameworks there, the data is somewhere there. What is the role of the processor today? What the CPU is doing today? So the role of the CPU today is just to bring the data to those accelerators and coordinate, the movement of the data from outside of the system into those accelerators. So we designed a new system. It's called AC922 deep learning system that has 4 or 6 GPUs, Volta GPUs inside, 40 cores, 2 terabytes of memory, all these kind of jumbo mambo numbers. But again, it's a very powerful system. Sometimes we have customers where they cannot stress the system. I'm saying, bring more data or create a better algorithm. So what is unique on this one, and we work with our partners NVIDIA and Melanos, there are 2 things that I want you to remember. One is that we interconnect those fast GPUs. GPUs is coming from a graphical processing unit for gaming, but they are being adjusted for this kind of things. And we have this NVLink technology here where we connect at 150 gigabytes a second. Those GPUs, the whole industry is using PCI generation 360 or 32 gigabytes per second. And then we have memory bundled 170 gigabytes per second per socket, which means that we are double than the industry on the x86. Why this is important? This is the GPU. So when you buy a system like this, 70% of the price is coming from the GPU. You have a GPU, right? I want one. Yeah. So they are very expensive. One, they have 5,000 core on range and a specialized core called tensor cores. Those systems, they can deliver from their own memory 900 gigabytes a second, almost 1 terabyte. You'll be amazed. Who will use that? Well, take a one data scientist, a system like this will not be enough for you. Because those algorithms, they're actually doing matrix multiplication over and over and over and over again. And you just feed the images. And if you want to have better results, you need the good resolution images, which means higher data. So the question was how we can really feed those GPUs faster. And we have this NVLink technology and this Power9 processor that we created with the Open Power Foundation to actually bring this kind of technology on the market. This is what I want you to remember. And then there is something else, it's another kind of accelerator called FPGA. It stands for Field Programmable Gateway Array. When we have customers that they say, well, I don't want to run my models in an expensive GPU, which is consumed 300 watts, I have to cool that. I want to run this in a system or a dedicated device, so I want to put the model here and get the results fast. Well, there is also this possibility where we can combine both of them. This one for inference, the other one for training. So, if you look on the software stack, you say, okay, I understand for the hardware, you have one single system, you have some accelerated storage on the back there that you can send you the data, but what about software? So we have the hardware layer, we have seen, so this AC922 systems, we call it Mule. Then we have flash arrays or parallel file systems like ESS. And then if you have devices, which by the way are remote location, you cannot send the data into a data center. There is no way to do that, unless you have a lot of money. So we use cloud object storage to store the data, and then when we have to process the data for deep learning, we use spectrum scale. So highly parallel file system that really can feed those GPUs faster. And then moving up to the stack, we have private cloud or public cloud if you want, depending on what you want to consume, or bare metal systems. So both of them, they can really combine and have the solution. And then a couple of deep learning frameworks optimized by IBM for this hardware, or open source framework that you can take it from the community, plus some other things coming from the research. We have as well a couple of projects called PowerAI Vision, the one that I use it, which is standalone product. You don't mess with this kind of thing, you get that installed and that's it. And then we have data science experience local, which is another project combining multiple data scientists and we use Anaconda for Python. So all this kind of work is actually using Python. I had a question yesterday if I'm using R. Is anyone using R here? Language? A little bit, right? So not so much. In general, it's Python. So we actually tied up with Anaconda, where you can have Anaconda, so Python with support for them if you want in the production. All right. So moving further, I want to explain a little bit some of our added value on top of the open source, because this is open source. It's called PowerAI Base. It's coming with the hardware free of charge, and we have TensorFlow with Keras, and so on and so forth. But what is unique here? There are two things here. One is distributed deep learning. When we try to use more GPUs in a training, how you do that? You will say, I'm using TensorFlow, I'm using gRPC. Well, the efficiency of using gRPC in general is 56%. So if you have a training running for 20 days on a system with 4 GPUs, you expect that if you add another 4 GPUs, the training will go by half. Bad luck, it's not. So IBM Research created a distributed learning library that we ship with all the systems, where we can scale stimulus with TensorFlow, Caffe, and PyTorch by just a single command. So that is giving you a 97% efficiency in scale. That's the first point. Then we have something called large model support, where we are working with large data sets. For example, in the image segmentation for brain tumors, 3D images. In general, they are so large that one GPU with 16 gigabytes or 32 gigabytes can actually take 1 or 2 images at a time. So not so much thing, but the large model support can do a lot of interesting things for you, and I will explain as well. And then we have a lot of libraries here, Nickel, Bazel, you want to combine TensorFlow stuff, and so on. So everything is optimized for the hardware, freely available on the Docker Hub, so you can take this by just a command on the system, and you can run on the containers if you want, or you can put this in the cloud private, it doesn't matter. From the operation point of view, if you have tried several times to use those frameworks, you know that it's a painful process to get the environment run. So we have a simple way to optimize all those environments with simple commands for the users. Then the large model support is actually explaining this. So if you have large images, they will going to be tied on the GPU memory. So what we allow, because we have this sampling technology here, which is 150 gigabytes a second, we can extend the model to the host memory to up to 2 terabytes. So we can have more images or larger model. Yeah? And the implementation is very simple. This is with Caffe. We have only 2 switches here, saying that if the image is bigger than 10 kilobytes or 1 megabyte, don't keep it in the host memory. Keep it in the memory, or keep it in the memory of the host. Put it in the GPU memory. And then we have a fraction saying keep X memory free available. The TensorFlow implementation is using the same large model support, and the way that we do it, we actually, in the backward propagation, we swap up some weights into the host memory, which is freeing up the space into the GPU memory for much more data. So this is something that is available starting with TensorFlow 1.8 and now 1.10. We submitted as well to the open source community. Hopefully they will embrace this officially. This is just an example of running with large model support on the hasty MentionNet, a system with 4 GPUs, training 3.1 hours, and by using LMS you can go to 40.9 hours, 40.9 minutes in the training, just with those enhanced images which are highly associated. So, who is using GLMs here? Logical regression, SVMs. Okay, so there are a lot of banks using this in reporting. When you go and get a credit, they are checking you, right? When they are checking you, there is an algorithm running like this in the back, trying to get the feeds and so on. So we had to take a look on this. What is the current implementation, the state of the art? Everyone uses skitlearn. So if you work with a data scientist, you say, this is my friend, skitlearn. It's open source. This is very good on sparse data support, so huge data sets, but has no GPU acceleration. So we actually look on the market, there's a PySpark, again, no GPU acceleration. TensorFlow implementation lately has inefficient GPU acceleration and limited data support for the sparse data. So IBM Research in Zurich actually create, we call it SnapML for all those GLMs where we actually cover all these cases. And there are 2 lines of code. You don't bother to read this, you'll get the slides, but in general, you import the library and then you say, use logistic regression or SVM on this GPU or this number of GPUs. It's that simple. So the result was a benchmark done on the 1.2 terabytes data set called TeraClick. You can find it on the internet, you can download that, where we're trying to predict the clicks on the website, where a person will click on the next second. And there is a good paper done by Google where they've done the same thing across 90 servers, no acceleration because they use skip-learn. And this is what we have done with 4 power servers. So from 1.1 hour training to 1.53 minutes by using just 16 GPUs. This is the power of accelerated computing today. All right. In distributed computing, I just explained you, single system, you can do a training on 16 days, where I was doing a training for automotive customers, couple of weeks, 27 days, and get nothing, and then grind again, and so on. But when you have more systems, you want to do it in a couple of hours, right? So it's very important to have an efficient way of scaling distributed deep learning. I have another 10 minutes, and then I will just okay, so moving further, we have the PowerAI Enterprise, which is actually another stack for the enterprise companies where they want to pay a lot of money for having additional things, like hyperparameter tuning. Because in general, if you don't have data scientists, you have 2 options. Buy smarter software or just hire more people to do the thing. So we had a couple of things, not much, like, for example, data model visualizing the training, optimization of those models. One of the questions was how we do the training. Here is another way where we can optimize the training if you're not a data scientist. So the system will actually, you can go and look on every convolution there, but then we'll actually try to recommend you some hyperparameters like the batch size, for example, if your model is underfitted, and those kind of things that you can go and pass to the training. This is coming as well from research, and we are pushing this into the PowerAI Enterprise to put together with the distributed learning of more than 400 nodes. So a lot of things that will come up. All right, so we have seen as well the PowerAI Vision. A couple of things in general that we are concentrating in PowerAI Vision. We want to bring together capabilities of image analysis, developer, and data scientists. Because in general, they don't cooperate and they don't work together well. So our goal was to create a single standalone system that we can install by just 2 commands. Everything is done by containers, where we can offer image labeling, graphic processing, video labeling, customer learning, image classification, and then to actually create the inference, whatever we have seen. So you have scene screens, the data augmentation, and then we have as well a way we call the inference server, where you can give a model to someone, say, here's my model, here's the container, we import the container, and the container will expose RESTful APIs and actually the protocol there to say, I'm waiting for images or video streaming to do classification or object detection or scale testing. So it will be much easier to build up. For the person that they really want to take this on the edge, to put it on cameras, to put it on places where you cannot put server, we are looking right now to bring on the market PowerAI Inference Engine, where we can take a trained model, and then we can optimize that model for FPGAs, and then create the Verilog files for FPGAs. If you are working with FPGAs, it's a nightmare. So we are trying to bring this very fast in a simple graphical user interface. So we can take a model from the data center and then you deploy that into an embedded FPGA, which is a camera, could be anything you can imagine, an embedded GPU, neural network processor, and so on and so forth in the future. So try to imagine all these use cases you have seen where a camera is sitting somewhere in a factory. That camera which is sitting there, in general, has to be connected to a server. If you don't have the room to put that server while you are doing it. So you have to use a camera that has an FPGA embedded where your model is running. So you don't have to stream the data, you don't need to have high bandwidth internet and so on and so forth. That's very important. So we are actually moving in this direction as well as some other kind of use cases. So if you look on the medical field in general, all the mammography part, all the computer tomograph part, etc. and so on, there are devices that have a computer inside. So ultimately, you can consider that you can have one embedded FPGA inside running on a PCIe bus, like a Ethernet card, where a model like this is running. So you can actually interfere there without the other kind of things. It's the same thing like the cars today, they have the firmware for the computer, there is a FPGA running there. And the reason to use FPGAs is as well is the thermal problem. So when you put those FPGAs in places where, outside where you can get 40%, 40 degrees outside in the summer, you have to cool them. And that's a problem. All right, hopefully I'm not a cat today. And if you have any questions, please let me know. You will have my email address. You can always send an email, or there's a team here from Italy. They speak Italian better than me. And you can always contact us. We have other partners that for startups that they want to integrate this kind of technology, and it's happening everywhere. It's slowly moving. Now we just barely try to explore this technology right now within the industry, in various places of the industry. And we have partners that they try to move from the traditional IT to this new kind of workloads. Even us within IBM, we are part in the cognitive group where we are trying to really shape or change the products towards to what's going to happen in the next couple of years. This will really revolutionize everything that we know today in the industry. Right? I strongly believe that this technology can really be used for a lot of things, especially by doing more interesting things with natural language processing, natural language understanding, and then we're going to have the enforcement learning that will come up. Right? Then the next wave that will come is spiking neural networks, specialized processors that will come up for AI, analog processors, combination with digital, who knows. Things will be very interesting for the next couple of years. Thank you very much, and I'm